Okay, hello. This is a video for CS 471, 571 operating systems at ISU, and we're going to look at some C programs that are going to be used as homework assignments as well. And the point of this is to review some of the stuff that we're supposed to already know. So this is a list of functions from the C standard libraries and some system calls in Unix that it is recommended you have in your brain as being able to use. So we're going to look at a few examples to refresh your C programming, and then I'll give you some assignments based off of this. Okay, so we'll start with there's 3 C files here. I will look at each one in turn. So we're going to start with just one of them. So I will first run this to see how it works. Okay, this is a program that expects a source and destination. So I'll give it copy.c and I'll call it copy new.c. All right, it ran. If I look, there's copy.c, 796 bytes. Copy new.c is 796 bytes. And if I diff them, there's no difference, they're the same. Okay, so all this program does is copy the first file into the second file. All right, now what you should do is pause the video and think, if you're writing a C program to do this, what is the code going to look like? Okay, so pause, think about it for a few minutes, jot down some notes. What are you going to need to do in order to do this? Okay, maybe you paused and thought about it. Now we're going to see how I do it. All right, so this is copy.c. I will go ahead and put in some comments here like we're supposed to. So at the top, this is Jeff Kinney. So what does this program do? I don't know. I could put a date here as well. So this is August 23, 2018 contents, and this is a program to copy a file, practice using C. Okay, so here we have our processing command line arguments. As usual, argc tells us how many arguments are there, and if we ran the program like .copy 471 source destination like we see here, this would be argument 0, argument 1, argument 2. So if we don't have 3 of these, then they didn't do it the way we wanted them to, and I write out a usage statement. And here I've used the write system call. We could have also done fprintf, std error, we could have done this as well using fprintf, and then we could put whatever we want to in the quotes there. Here I've showed you doing it using the system call. Practice using C using system calls. Okay, so the system calls are a lower level function that's going directly to the operating system. So I'll say note that write is a system call, goes directly to Unix kernel. fprintf is a library function which uses write, but it allows us a nicer interface. If we look at write here, we just give it a pointer and how many bytes to write out. What's the difference between that and fprintf? fprintf, we can tell it that we're outputting an integer or a floating point number or whatever, and it converts that into characters. This, we would have to do that conversion somewhere else and write. The write system call just gets a pointer and a number of bytes. That's it. And the first parameter here, what is that? That is a file pointer of which file to write to. One means standard out. So every process has a file open that's the file descriptor is 1, so 1 means std out in call to write. Okay, so if we do have the right command line arguments, then let's go ahead and use them. So argv bracket 1 is this source. We're going to open that for reading. This is the open system call. So we give it a file to open, and this is read-only. If you don't remember your parameters, so you could pause, or while I'm talking here, you could look up the help for open to see what these what the different options for the parameters are here. All right, so we try to open the file for reading. The help on open tells you that if you get a -1, that's an error. So we just print out that there was an error if there was an error, and exit. Okay, the destination, I'm using the argument at index 2, so this is 0, 1, 2, that's the destination. I'm opening it for writing, and if it doesn't exist, I create it. These are bit flags, so I OR them together. This write only, that really is going to be maybe, I don't know what that evaluates to, but it's maybe just 1 bit out of the flag, and this is a different bit, and if you OR them together, then that's both bits that are going in to tell open that I want to write and I want to create it. And what was this one? I don't remember. That is, let's see, the third thing there is the mode. So the mode, some of you remember what that is for. SIRWXU. Oh, okay, so that's the, if we're creating a file, what are the permissions given to the file? So this is read, write, execute for the user. Right, so user has read, write, execute access to this file, that's a new file that's created, and others don't. So this is another difference between using the open system call versus, so we'd say note open is a Unix system call, fopen is not. So fopen, you don't get to decide what the file permissions are, but it does some other nice things, like you can use fprintf. Open is bare bones, you're talking directly to the operating system, and something nice there is you have extra things, extra control. So you can specify the permissions, you can specify other things in the flags as well. All right, so if that works, then we have a source file and a destination file. Both of those are file descriptors, which are very similar to file pointers. All right, if they're both open, what I want to do is loop through the source file, read bytes from it, and write them to the destination file. Okay, so we're going to do a read that's similar to fread, but it's a system call. So we give it the source file descriptor, a place to put information, and how much do we want to read. I'm going to just do one character at a time. I read it. The count is going to be how many were read, hopefully one, and then I write those out to the destination as long as I keep reading bytes. When it's done, then I close both of those. So that's the copy. Let's see how we're doing on time. We'll go ahead and show the next program. So what you want to do is maybe pause the video and just kind of look through that again to make sure you get all of that, and look in the man pages if you need to look up some of the parameters. All right, let's look at head. Okay, if I run it, nothing happens. Now it seems to be printing out what I typed. Let's try running it with a parameter. Okay, so if I give it a file name, it's printing the first so many lines. Okay, so if I give it a parameter, it's printing off of that file name. If I don't give it a parameter, it's reading from the keyboard and printing the first 10 lines either way. Okay, so this so what does this do? So this prints first 10 lines from either a file or a standard input. And in this one, I think, let's see, we are using file streams. Practice using file streams. Okay. So here we're using fopen, fprintf, fgetc, and printf. All right, so those are file stream functions. They're from the C standard library. They're on top of Unix. Okay. All right. So first thing is to check the command line arguments if there is an argument. So that would be if they ran it like /head471 copy.c. If they ran it like this, then argc would be 2. Okay, so if that's the case, then we try to open a file to that first argument. We do it with read access. Fopen returns null if there's a problem. If there is, then we print an error message and exit. Okay, so that's if there is a command line argument. If there's not a command line argument, then I'm going to read from standard in, and I can do it like this. So I have a file pointer, I can set that to standard in, and then use F, and either way it's either going to be standard in or this file. Okay, so then I'm going to read one character at a time, using fgetc to read one character. I save that into an integer. That integer value is EOF when things are done or if there's an error. So I read that character, I save it into an integer. If it's not EOF, then I'm going to be inside of here and I'm going to do something with the character. If it's a new line, I'm keeping track of how many lines there are. No matter what, I'm going to print it. If I get to more than 10 lines, I break. Okay, so this is your example of using the file stream functions, and you could compare and contrast the two. So the copy, this is using file system calls, doing similar things, but the parameters are different. Okay. We're going to go ahead, we'll finish up our 3 examples by looking at run.c. This one's a bit more interesting. Let's try to run it first. First of all, you might pause and recap head.c, which if you're watching online and you do not have access to the web server, probably maybe this link is still valid, and then the examples are in this directory here, and you could look at them this way. All right, so moving on to run.c. Now I'm going to run 471. It prints something. I say hello, it says error on exec CVE. I say ls, it says error. I do that, /bin/ls, and it printed out like from ls. All right, let's run it again. Hello, quit. Let's see, what else is in /bin? Let's say let's just leave it. That's good enough. All right, let's go ahead and take a look at this run.c. So it appears to be reading something that I type and trying to run it as a command. All right, so let's first get our comments in here, author B. So program to read from keyboard, read a command from the keyboard, and execute it. So this is practice using fork and exec VE. All right, so those are 2 system calls in Unix, and the basic shell that we use, that's the outline of the shell. Is you read something from the keyboard, it's a command, run it, and running it uses fork, and we can take a look at the code to see what that actually means, and then we want to execute the exec VE. Actually, let's take a look at exec. So this is the system call that we get in Unix. So this is what Unix gives us that allows us to run a command. All right, so exec VE executes a program pointed to by the file name, so that's good. If we're sitting here and we say ls, it's actually going to find out that that's a program that lives in /bin, so it's going to find that program and we want to run it. All right, that's good. This exec VE does that. Great. So this causes the program that is currently being run to be replaced with a new program. So read that carefully again. This causes the program that is currently being run to be replaced by the new program. Replaced. Okay, what program is running right here in this window? It's the shell itself. It's the program that reads my commands. Okay, so the shell is running. That's exec VE. If that's what happens, then it's going to take my cell, and instead of the shell running, it'll be the ls program. That's good that it runs the ls program, but there's an issue. And the issue is it replaced the shell. The shell maybe is no longer running anymore. And let's take a look at something else over here. Let's look at the return value from execve. So here's the return value. When it's successfully run, it does not return, ever. If there's an error, it gives a -1 return. Okay, so if I have execve in my code, which I do have in this code at some point, so when I get to this point in the code, then nothing happens after this. So what happens is the command will run. When the command finishes, it doesn't come back here. The program would just be done. Okay, so if we use execve, then we never get back. So this is interesting. Note that execve never returns if it is successful. That's kind of interesting. But what if we want it to return? Right, there's a way, the designers of Unix have given us a way out of that. So what we should do is we fork, so that is we create 2 copies of our program. Okay, so we do that. One of the copies of the program does execve. The other copy of the program waits for it to finish. Okay, so we have our program running. We create 2 identical copies, nearly identical. One of them is going to run the command. So one of them is going to run this /bin/ls. The other one's going to sit there and wait for it to finish. Okay, Unix gives us what we need to be able to do this. So fork is something that we can do. One of the copies runs execve. The other copy of the program waits for it to finish. And there's a system call for that as well. So let's go ahead into the code now. You might want to pause. If you want to pause and just read that a few more times, that might help. But let's go into the code. So I have a do here, so we go in. There's some string character array command, length equals 0. At that point in the command string, I put the null byte and I print a greater than, which is often used for a prompt. Then I have a loop here. I'm going to get char. That comes from standard input from the keyboard. As long as that's not EOF and I haven't read a new line, so I'm going to keep reading until I get enter. As long as I haven't gone past the end of my space that I have allocated for my string, I go ahead and do command bracket length equals character. So the new character goes in the end of the command string, and afterwards the length is incremented. The ++ afterwards, remember that if I do it like this, it'll increment before it does the command. Square brackets, if I put it after here, then it does this statement and then increments. You could pause and make sure you think that that's the right order to do it in. All right, and then I put the null byte back on there. If the character coming back was EOF, then that would mean, let's see, run 471. If I type Control D, that's the EOF character, which is normally meant I'm done. Or that, yeah, that makes the EOF character come through. Okay, or if they say quit. So there's a command there. If it's just exactly quit, then break there stops this do loop, and after the do while loop there's nothing. Okay, so if I run 471 and quit, it just is done. All right, so that's in my program. That's not a quit command, it's me checking for it. Here we split, so this is create two nearly identical copies of the program. And the rule for fork is that one of the copies will get a return value of 0 from the fork call, and one of the copies gets a non-zero, greater than 0. Okay, so we're going to have two identical copies of this program now. The only difference is one of them gets a value of 0 in this P, and the other one gets an identifier. So the person that gets a 0 is considered to be the child. That's the convention. All right, so the child is supposed to execute the command. That's here. We have exec.ve as a function that takes this command. It also takes an argument list and an environment list, which I've just initialized to be nothing there, just empty lists. And it runs, and if it's successful, so the child is running, if this is successful, it never returns. Okay, if there's an error, it does return. Okay, so the child would be sitting there right, the child would be sitting there, this wasn't successful, so we really should probably exit here. Right, so then no matter what, the child's going to exit. And the parent really probably shouldn't. Okay, so if it's successful, the program will run whatever this command is. If it's not successful, we get an error, but we don't really want that copy of the program to continue. We don't really want two copies of this program reading in commands. We really just want one of them, so we're going to exit. The way it was before was probably a bug. So /bin/ls/bin/ls hello /bin/ls. It keeps going until we either do Control D or quit. Okay. Now that's what the child does. The child basically runs this, and that's it. Or there was an error, and then we just bail out. So the parent gets this P. So the P that it gets from the fork is an identifier of the process. So we have the parent process and the child process. They both have identifiers. If we look, let me go over here. Let's see, I'll go right here. So if I top here, so this is running on my Mac now, not on the server. But this is a list of programs that are running, and each of the processes has an identifier that identifies the program. So the command that was run was top. There's MD worker here. There's multiple different copies of MD worker. They all have their own different process identifier. All right. So this P that comes back from the fork is that very thing, is that process identifier that if we look inside the operating system, somewhere inside of it, it has a list of all the processes. You could think of it as like a spreadsheet where one of the columns is the identifier. So it has this number in there, and then I could get information about that process if I wanted to. one of the things that you can do with a process identifier is a wait PID. Okay, so a wait PID wait PID here says wait for a state change in a child of the calling process. So we're going to wait for the process that's this PID, wait for the state to change, and the state is whether it's running, yes or no, whether it's done. Okay, so I'm going to wait for the status to change, and that's going to change when that program is done. And the reason that I want that, so I'm going to do /bin/ls. So that program's going to run, and it's going to print to the screen. While that program is printing to the screen, I don't want my shell reading input. That wouldn't make any sense if it's doing something here, and then I'm also going to be typing. Okay, so the parent really should wait, and I could check what this status is, but I'm not doing that there. All right, so that's this program where we've looked at fork and exec_ve, and we also used the system call and wait PID, right? Those are three system calls that we used here for good fun. And this outline of a program we have here is the start of a shell. So you could start going from here and adding features to make it into a more full-featured shell. That'll be it from this video. Have fun.